Started. So yesterday, let's just remember where we were since it's been a long day. So yesterday was all about kind of what we can call monomorphic functional programs. And okay, why don't we pause for a second while everyone comes in. Okay, let's get started. So yesterday we were talking about monomorphic functional programs, and hopefully through yesterday's lectures and through some of the work you were working on last night, you've gotten a sense for how some basic ingredients like function types, product types, sum types, some inductive types like nat all fit together to give a functional programming language, how we can define the static semantics and the dynamic semantics, right? So static semantics is the typing judgment, dynamic semantics is stepping, and so we set up all that sort of syntactic machinery. And then the main point from yesterday afternoon was that we can define two notions of equality, logical and observational, and show that they coincide. And a few people asked me, like, why do we want these two notions? How do we use this to verify programs? What's going on with that, right? So the main point to remember is that the reason to bring up observational equivalence is that it's what tells you essentially that you can replace equals with equals. And the reason to bring up logical equivalence is that it gives you a type-directed way of proving that two programs are equal. So the one example that we did was something like you take plus and flip plus, you show that they're equal using logical equivalence, which gives you a nice way to sort of reason about when two functions of type int or int or int are equal. And then from that, you get that you can replace flip plus with flipped plus in any context. Okay, so what we're doing today between my lecture now and Bob's lecture later this afternoon is to take this whole story and move towards what's called polymorphic functional programming. And to boot up on what polymorphism is, which is our main goal for this morning, what we're going to do is we're going to do a few examples of the kinds of programs that we want to reason about and kind of informally talk about the kinds of things we want to prove about them. And then this afternoon, Bob will go through the formal machinery that lets you do that. So just to boot up on polymorphism, here I wrote a couple of simple list functions, which you probably have written if you've done any functional programming. One that takes a list of integers and produces a list of strings. How does it do it? If the list is empty, then empty. If the list has a thing and some other stuff, convert the first thing in the list to a string, and then recursively convert the rest of the stuff. And a good exercise, if you haven't looked at the chapter on lists in PFPL, is figure out how to write a rec construct for lists that parallels the rec construct for nats that you've all been working with that captures exactly this pattern of recursion, right? The most fundamental pattern of recursion on a list is, well, if I'm doing a recursion on a list, then I say where the empty list goes, and I say what to do with a cons in terms of the head and the recursive call on the tail. right? So that's exactly structural recursion on a list in parallel to structural recursion on a natural number from last time. So here's another function that looks pretty much the same. If I'm adding a number a to everything in a list, then if the list is empty, then empty. Otherwise, if it has a head and a tail, add a to the head, recur on the tail. Okay, so it's the same pattern of do something to the head and then recur on the tail. If we want to not write repeated pieces of code there, then how do we make one function that does what both of these functions that are on the board do? How do we parameterize? How do we abstract? How do we make more concise code? Well, what are these both an instance of? Map, right? So there's a function called map, and the idea is that it's going to be a higher order function, which will take a function and L, which is our list like above, and if L is the empty list, then what's the answer? Well, what's the answer for the empty list in both of those? It's empty, so there's nothing to abstract there. If it's a head and a tail, then what do we want to do? We want to make our recursive call on the tail, of course, because both of those functions recur on the tail. And what do we do to modify the head of the list? Call f on it. Okay? So if we are to define this one as an instance of map, then what is it? Two strings of L is mapping something on L. What's the something? It's the two-string function. And if we are to define this one, then add of LA is mapping something on L. What's the something? Well, it's the function that takes an x and adds, which way did I do it? Adds a to x. Okay, so you see how if I have a placeholder f that stands for a function, then on the one hand, plugging in the two-string function gives me two strings. Plugging in the add a to each thing gives me add. And now I've got one function that subsumes both of these. OK, now let's think about the types involved. What is the type of this argument to map? Takes an int, returns a string. What is the type of this argument to map? It takes an int and returns an int. So this is the idea of polymorphism. We would like to use the same code map at two different types. So what we want to do is we want to write down the schema that map has, which sort of relates how the different types fit together. So if f takes something to something, and L is a something, then the result is a something. So what should I write there? A list. And what should I write there? B list. OK? So if you give map a way to transform an int to a string, and then you give it an int list, it gives you back a string list. If you give it a way to transform an int to a string and you give it a string list, then it doesn't apply to an int, give you back an int list, right? There's coordination between the types involved. And so what we want to do is we want to capture that as something like this, which says the polymorphic type of map there. So the idea of polymorphism is that this type, which we can write as, let me write it a little bit more formally as, if you give it an A arrow B and then an A list, it gives you back a B list. That works not for specific A and B, but for all A and for all B, right? The idea is that no matter what A and B you want to pick, if you pick two A's and B's, it does that. Okay? So what we're going to try to capture in a definition of a programming language is this idea of polymorphism or generality in a type. Okay, and so let's now look at what that'll look like if we define a language with this kind of idea. So what we're going to do is to, and then I should say, here we should note that we're choosing the two types here to be int and string. And here we can note that we're choosing the two types A and B to be int and int, respectively, right? Each time I use map, I might say, here are the types I'm using at this particular use of map. OK, so what does this look like if we try to make a language out of it? Well, the key new idea that we need to make this work is the idea of a type variable, which is going to be just like the variables that we've seen in programs yesterday in the various languages that we studied, except now we're going to have variables in types. So the idea is that we'll have a judgment. Delta proves tau is a type, where delta consists of assumptions. T1 is a type through T sub n is a type. So for example, it will be true that assuming that A is a type and B is a type, A arrow B, arrow A list, arrow B list is a type. Okay, so the idea is that this stuff, the stuff that went in the body of map, is a type, assuming that A stands for a type and that B stands for a type. So that's the new ingredient that we need there. And then the inference rules for that will be things like delta proves tau is a type, delta proves sigma is a type, therefore delta proves tau arrow sigma is a type, right? So to make a type depending on some variables, I can take two types that depend on those variables, put an arrow in between them, and then I've got a new type that depends on those variables. So for example, to show that this is a type, it suffices to show that with variables a, b, I have a arrow b being a type, and that with variables a, b, I have a list arrow b list is a type. Okay, so there's a bunch of rules that just sort of go structurally over the type. And then the interesting new one will be to show that for all t dot tau is a type in delta, we assume that t is a type and show that tau is a type, right? So to show that a for all quantifier is well formed, you add an extra variable and then check that the type inside of it is well formed. Okay? And because of our convention that variables are pronouns, like Bob was talking about in the hands-on session yesterday, right? We'll know it's sort of taken for given that t is different from all the variables that are in delta, right? That's just sort of a basic property of variable binding that will assume that when we make up new variables, it's always kind of a fresh thing that doesn't interfere with anything else that we have around. So now that we've got the judgment of something being a type depending on variables going on. What we want to do is we want to talk about how you would write code like map, and let me write in map A, B there, that abstracts over some types. And there's a very nice, simple idea, which results in a system called System F, which is due to Girard and Reynolds, who independently invented it in, I think, 72 and 74. And the idea here is that we will allow, essentially, lambda and application for type variables. So yesterday we got used to having lambda and application for program variables, right? When you wrote a function to do addition in Gödel's T, what it did was it was a lambda that bound a variable standing for its argument. The only new thing here that's going to give us polymorphism is the idea of having lambda and application for variables that stand for types as well. So here's what that looks like in syntax. We have that if we want to show that, so it's customary to write this as a capital lambda, just so you can tell by looking at the term whether you're talking about a term variable or a type variable. So we'll have capital lambda t dot e has type for all t dot tau if extending the type context with the assumption that t is a type, keeping the term variables the same, e has type tau. And then the application will say that if we know that e has type for all t dot tau, and we come up with some specific type sigma that we would like to choose it to be, then e applied to sigma, and it's customary to write that kind of application as a square brackets there, has type tau, has type plug in sigma for t in tau. OK, so let's think about that for a second. To make a function that abstracts over a type, what you do is you bind a type variable, just like functions that abstracted over values bound value variables. To apply such a thing, a polymorphic function, what you do is you pick a type that you would like it to work at, and you apply it to that type. So for example, map would really start out capital lambda A, capital lambda B, dot lambda F colon A arrow B, dot lambda X colon A list, and then would have some code. And inside of that code, eventually you'll get down to a recursive call that looks like map applied to A applied to B, F, X's, like that. So this here is the type application, and this here is the type abstraction. And in many languages, you might not write the type application and the type abstraction, but for the basic calculus of polymorphism, we're going to make that explicit. OK, good? Questions on that notation? OK, so now what are the dynamics? Well, they're actually pretty easy. So suppose I have a type application like that. How should it step? If I run the function position for a step, then I can put it back together. That's kind of my search rule. And then suppose I have lambda t dot e applied to some type sigma, what do you think that steps to? Plug in sigma for t in E. OK. And so the substitution principle that we need is that if delta, assuming t is a type, proves tau is a type, and delta, assuming t is a type, gamma proves e colon tau, then where, in this case, that type can occur over there, and delta proves sigma is a type, then delta gamma proves plug in sigma for t in E has type plug in sigma for t in tau. Okay, so the new thing relative to what we talked about yesterday for the substitution principle is that if you do a substitution into a term for a type variable, and the type of that term has that type variable free as well, then you plug in, not just plugging into the term, has type plugging into the type. Okay? Which is to say, if you take map and you plug in for a here, then the type of it is just plugging in for a there. Right? If we take a to be int in the term, that has type, take a to be int in the type. OK, good. So now this little calculus called system F, so system F is really this, I should say, plus the rules for, well, not plus because I don't mean the sum type, with the rules for the arrow type, the function type that we talked about yesterday, so that you can have something like for alls and arrows all together. So this little calculus has an enormous amount of power. There's a lot you can say in this. And so I want to do some examples to draw out some of the things that you can say in this. OK, so first of all, we've got map. Second of all, I want to make a distinction between two kinds of polymorphism and talk a little bit about what kind of polymorphism we're talking about here. So when people talk about polymorphism, that is functions that work at many types, there's kind of a divide between what I'll call intentional and parametric. And the idea there is that intentional means, well, let me say parametric. Parametric means the same code at many types. And what I'll call intentional means different code at different types. So if you think about something like map, we're really doing the same thing, no matter whether we call map with int and int, or int and string, or string and int, or whatever. No matter what we do, we're taking a function and a list and applying the function to each thing in the list. So that's what an example of parametric polymorphism. If you want an example of intentional polymorphism, that would be something like you write a function that works for many different types, and that function says, suppose the type is int. In that case, I'm going to do this. Suppose the type is string. In that case, I'm going to do that. Okay? So there you would need some sort of way to case analyze a type at runtime in order to make those distinctions. So, yeah.
But that limits the amount of types we can apply it to, doesn't it?
It does, yeah, right. So it means that you expect sort of a closed world of types if you're going to have that kind of thing. Yeah, right. So you expect that you can enumerate all of the types and give cases for them. Or you might have some kind of catch-all case, which is like, if it's some new type that I don't know about, do that. Okay, yeah.
That would be kind of parametric then.
Kind of, but the distinction I really want to make is that here there are more programs that you can write, right? So like you can write something that looks like the type of map, but does different things depending on whether A is int or A is string. Here, the key point we're going to draw out today is that you have more theorems. Okay? There's more that you know about a program just by knowing its type if you're talking about parametric polymorphism. So there's this sense, if you've programmed in ML or Haskell or other strongly typed functional programming languages, that once you get your program through the type checker, you're kind of most of the way there, right? There's relatively few bugs that you'll find after you get it through the type checker. A lot of that sense is coming from this idea of more theorems from parametric polymorphism. Okay? So let's think about an example of that. What do we know about map just by virtue of the type of map, not the code for map, right? So pretend we hadn't written this yet. What can we say about any function of type for all A, for all B, A arrow B, arrow A list, arrow B list? Okay, it has to apply the, well, function foo f underscore equals empty list, right? Yeah. Mm-hmm. Exactly. So if we're going to work uniformly parametrically in the types, then this piece of code, if it's going to work for all B's, has to treat B as an unknown. It has to treat A as an unknown. Therefore, if it's ever going to produce a B, how can it possibly do it? Well, the only way to make B's is this method of making B's that you provided as input. Therefore, every element of the resulting list must be of the form f of A for some, or let me not call it A, f of x for some x colon A in the input list. Why? Well, if it's going to be the same code at all types, then it has to make B's from knowing only that you can make a B from an A. Where can it possibly get an A from? Well, A is a type variable. If it's going to work parametrically uniformly in A, then all it can possibly do is grab an A from the list and kick out something there. So we don't know that it's exactly map, right? It's like you could shuffle around the elements of the list. You could duplicate some. You could drop some. But the type basically tells you some property that's approaching the spec. OK, next example of that kind of thing. Suppose we have a function, I'll call it R of type for all A list, arrow, A list. What can we say about that one? It's kind of a special case of what we just said. Yeah.
All the A's from in the return must be appropriate.
All A's in output must come from input. Right? If I was writing a specific function of a specific type, like int list, arrow, int list, then I could include something in the output that's not in the input. Right? I could throw in a 0 or a 7 or whatever. If I'm writing a function from strings to strings, I could throw in the string high that didn't occur. If it's going to work uniformly, and I have no way to build A's besides, well, no way to build A's, I just have a collection of them to start with, then I know that everything in the output must come from something in the input. Okay. So that's another kind of idea here, that because this language gives you parametric polymorphism, somehow we should know this without really having to prove it. Or somehow we should know this without really having to prove it about each specific function, just by knowing what type the function has. Okay, so this was a way to get to the next thing, which is, now suppose I have some R like that, and map defined not just of map's type, but actually defined as map. What we can prove is that for any f, which takes tau to sigma, some relationship about R and map and f. Okay? So suppose I have a function f that takes taus to sigmas. Then here are a couple of different things I can do. I can start with a tau list and make it into a sigma list. How can I do that? That would be map tau sigma f. Okay? What else can I do with a tau list? I can return a tau list. Okay. Well, there's lots of ways I could do that, but which way do you have in mind? Okay, so I could do like the identity. Yeah. Okay, that's not the one that's going to give me the diagram I'm shooting for. R applied to tau is a function from tau lists. Okay. What can I do on the bottom here? R applied to sigma. What can I do on the right here? Well, what do I get? Sigma list. What goes there? Okay. So it will turn out that that diagram commutes. Okay. Ed talked yesterday about commutative diagrams. What does it mean in syntax that that diagram commutes? It means that for any L of type tau list, we have that R of tau applied to L, right? So if I start with an L there, send it along that, and then send it along that, is the same as if I start with my L, send it along F, and then do R. Okay? So just as an equation between terms, the diagram commuting just means for any element of the source type here, L, if I go around that side or go around that side, then I get an equation. Okay? So is this plausible? What did we just say? Why is this true?
Whatever R does, it's going to do it to both tracks, right?
Mm-hmm.
So even if it's reorbiting the cross, it'll happen both ways.
Right. So what R does, right? Remember what we said is R is every element in the output of R comes from the input. That is, R rearranges the input in some way, maybe dropping some things, maybe duplicating some things, shuffling around the order, etc. If I rearrange my tau list and then transform every int in the tau list into a string, or do some map, right, that hits each element of the list after rearranging with a function, then what I get is the same thing as if I had first hit everything in the input list with the function, transformed it, and only then rearrange them. And why does that intuitively make sense? It's because of this idea that R is really the same code at different types. If you rearrange an int list, then that's like the rearrangement you apply is the same rearrangement as if you had rearranged a string list after transforming it into strings. Because you can't do a type analysis and say, if A is int, then rearrange this way, otherwise rearrange that way, right? So because of this parametricity, the idea is that the rearrangement has to be the same, therefore it has to commute with transforming the elements of the list in some way. Yeah.
So tau doesn't rearrange at all.
So tau is a type. Map doesn't rearrange at all, right? Because remember that we're not talking about, good, so like we're not talking about any function of this type right now. We're talking about specifically map, which specifically keeps the list in order and just hits things. Yeah, yeah. So this is not a theorem about any A-list, arrow A-list, and anything of maps type. It's a theorem about R itself and map. Good question. Other questions?
Why is this important? Why map doesn't rearrange?
It might still be true, actually. OK. Exercise, is this true for anything of maps type? Yeah, I don't know. So like, I only had it in mind. I've only proved it for map is all I can say. So good question. Yeah.
Wouldn't it not be true because if map list, the next function R could make anything different depending on if there's an odd or even number of elements in the list?
Yeah. Yeah. OK, that's a good answer to the exercise. OK. I think. I don't know. It's hard to do it when you're standing in front of a room. Anyways, let's. So the conjecture was that because something of maps type could be sort of non-parametric in the length of the list, if R dropped things, then it might make a difference. I don't know. Let's table it till the hands-on session, since there's a few more things to get through. OK. So one point I want to make is that this square that I just drew is something that you'll see later on in Ed's lectures. So what we just said is that yesterday Ed introduced the notion of a category, and in particular the category whose objects are types and whose maps are functions. And then the idea of a functor, which was a map between categories. And in particular, list will be a functor from types to types, if I write type for this category up here, because the idea is that list sends an object that is a type tau to a type list of tau, right? And list also sends a function from taus to sigmas to a function from tau lists to sigma lists. Well, what function is that? Map tau sigma f. Okay, so if you unpack the definition of a functor that Ed introduced for this particular category, then the objects are types, the maps are functions. List sends a type to a type, that is, given a type like int, it creates the type int list. And it sends a function to a function, that is, given a function from taus to sigmas, it creates the function, a function from tau lists to sigma lists. What we just drew is what's called a naturality square for what's called a natural transformation from list to list. So there's a notion of, just like there's a functor is a notion of map between category, there's a notion of map between functor. And the right notion of map between functor is exactly something like R here, which is to say, for any object, tau or sigma, it gives you a map between the instances of the functor. And those things are related by the functorial action of the functor itself. Okay? So if you haven't seen much category theory before, then think of this as just a little bit of foreshadowing of an example that when Ed gets to this stuff, maybe on Thursday, you said? Yeah, on Thursday, look back at this one as kind of an instance of this concept of natural transformation. And this corresponding, I bring this up because this corresponding kind of square, right, will, in the hands-on session problems for today, we're going to want to draw very similar squares, but for types other than list here. It's going to be a square that's going to look a lot like this, but for different sorts of types. And so I wanted to point out that what we're talking about here is sort of an instance of a more general setting. OK, so how are we doing? Good. Yeah. OK, so I want to pause on system F for all types for now. So that's like a little bit of an introduction to that. Yeah.
Did you say that?
Yeah.
Did you say that that square can be used for any R of that type?
For any R of this type, and for map specifically, this square commutes. Yeah. OK. So the question now that I'll leave dangling is, how would you possibly prove something like this? Because the tools we developed yesterday of reasoning by induction on the type or something like that don't really give you, with what we talked about with, well, to reason about a function from int list to int list, you do something. And to reason about a function from int list to int list to int list, you do something else, right? There was sort of this induction on the type. That doesn't tell you yet what to do with these kinds of things. And we're going to need, basically, enough juice in our way of reasoning about these sorts of things to be able to prove something very high level and abstract like this property, that any function of such and such a type must have some particular structural property. Okay? So this is going to be what we'll talk about in this afternoon in terms of techniques for doing logical equivalence with polymorphism. So this is the motivating example, a motivating example for this kind of thing. It's a kind of thing you might want to prove, which requires a new way of thinking about these sorts of types. So Bob will get to that later. Okay, so what I want to do next for the rest of the lecture is to kind of dualize this and talk about what are called existential types. So I'm using the kind of suggestive for all or universal quantification notation and lambdas and applications in system F here. There's a very symmetric notion of what's called an existential type. And the idea with an existential type is that it corresponds to what you might know as modules or abstract or private or hidden types. So in some pieces of code, you want to sort of draw a boundary between the implementation of some module and the client. And a typical case will be you'll want some sort of abstract types mediating that boundary, the idea being inside the implementation, you know what these types are. Outside the implementation, those types are hidden from you. Therefore, you get nice properties like the client can't break the invariants that are established by the implementation, or the client type checks no matter what implementation you plug in. Okay, so as an example, here's the simplest one I could think of. We're going to have a module for counters. Which is going to look like this. There's some existentially quantified type t along with the following operations. 0 is a t. I guess use that notation. Increment takes a t to a t, and value takes a t to a net. Okay, so what I'm trying to describe here is a module that has one private type, which I'll call t, and 3 operations. Think of t as the representation of a counter. 3 operations on counters. There is a 0 counter of type t. You can increment a counter, that is, you can add 1 to the counter. And then you can ask for the counter's value and say, please tell me what the current value of the counter is right now. Okay? So this is really, a very baby abstract data type, but it's enough to kind of introduce the ideas that we want to introduce. So here are 2 implementations of this abstraction. So I should say that what I just introduced was an example of, well, there is a new type exists t.tau, which is well-formed, assuming that t is a type, tau is a type. OK, so now here are 2 implementations of this counter module. How do you implement a piece of code with a private type supporting some operations. So now like we're going to be on the implementer side right now. What should we do to make such a thing come into existence? We pick what the private type is actually represented by. And then knowing that representation, we implement all of the operations. Okay? So what could we take t to be? Let's come up with the simplest possible thing that we can think of. Take t to be nat. In which case, what is the 0 counter? It's just the 0 of the natural numbers. What is the increment operation on a counter? What is the value itself? Okay? So why does that type check? It type checks because when we take the private type to be something specific, now, for example, increment has to have type nat arrow nat because we've chosen t to be nat, and we type check the body knowing that t is supposed to be that. So here's how we'll model that. Delta gamma proves pack tau, or let me call it sigma. Pack sigma e has type exists t dot tau if delta proves sigma is a type and delta gamma proves e sigma for t in tau. Okay? Which is to say, take t to be, so the idea of pack sigma e is take t to be sigma, and then implement e having plugged in sigma for t, which is how you know that t is sigma in the implementation. So this idea here is that it would be something like pack nat, and then we would give a record value. 0 goes to 0. Increment goes to lambda x successor of x. Value goes to lambda x x. Okay? And for type checking purposes, we might want to annotate the term here with the t dot tau, but when I write the examples, I'll leave that off. Okay. So that was a very simple-minded implementation. Let's come up with a better one. Take t to be list of, okay. Where are we going with this? Okay, so nat from yesterday was unary natural numbers, right? Natural numbers where the size of the data representing a natural number is proportional to that number itself. List of unit is also isomorphic to unary natural numbers, right? Where empty is 0 and consing the empty tuple onto a list is successor. Okay, so we could do that, like that's totally true, but I want something that like gets a little bit, a little bit more of a gap between the code than this one. So what might we do to improve the efficiency of our counter? We might want to represent our counters in binary instead of unary. For simplicity, I'll take binary to be some sort of list of bits so that we can work with it as lists, but it could be like packed into a word or something like that. Okay, so the idea here is that our first implementation will be unary. Our next implementation will be binary. Okay, so what we would say now is pack list of bit with 0 is defined to be something, increment is defined to be something, etc. So what should we take 0 to be for a list of bits? Well, there's many choices, right? Like if you're going to implement binary numbers with lists of bits, then empty list, list of 0, 0, et cetera, right? Like you could have many different representations. I think a nice convention is that we can maintain the invariant that none of our lists of bits have any trailing zeros, right? We'll have to figure out which order the bits are represented in when we do this, but like you don't write like 0, 123 for 123, right? Like we tend not to have leading zeros there. Okay. So how should we increment? Well, let's say most significant bit is last, just as a convention. Now, that'll make increment fairly easy. So how do you increment a binary number if it's written out as a list of bits? So if we want to increment, add 1 to a binary number, and it's empty, then what? We just want 1 bit. Or if we want to increment a list with a 0 at the front of some bits, then put 1 at the front. Or if we want to increment a 1 at the front of some bits, then put 0, but carry the 1. Okay? I mean, so, for understanding existential types, the code we're writing here doesn't matter, right? The point is just like, there's some fancier representation, right? This is just supposed to illustrate the idea of we can have an extremely straightforward, slow implementation, and then a faster implementation where we have to be a little bit more clever. Okay? What is the value function for this? I won't write it out in full detail, but it's lambda b's dot, essentially the sum from I over I of what? 2 to the I times like nth of b's at I or something like that, right? Like we're representing a number in binary where it represents successive powers of 2, so you do the multiplication and you figure it out. Okay, good. So the basic idea is we've got a reference implementation and a faster implementation, at least uses less memory, etc. And we would like to note that both of these have type counter because they're both of the form pick t to be something and then make some operations. Okay? So what we've got here is 2 packages of code that implement the same interface, right? There are 2 implementations of the same wavy line there representing an interface, which both have type counter because, right, so like before we had polymorphism, before we had existentials, it would be weird to say that this function has the same type as this function because in fact they have totally different types. But when you're talking about relative to a private hidden type, right, that's the type we chose in the pack, these 2 things correspond. Okay, so now what we've got is an example of the rule for using an existential. The rule, or for creating an existential. The rule for using an existential is a little bit complicated, but let me write it on the board. If delta gamma proves sigma is a type, and delta gamma proves E1 colon exists t dot tau, and delta t is a type gamma x colon tau proves E colon sigma, then delta gamma proves open Tx equals E1 in E has type sigma. Okay, what does that mean? A client of counter looks like open t, comma, and then if I use some pattern matching for records, I have a 0, I have an increment function, I have a value function, equals some implementation in some code that uses 0 of type t, increment of type t arrow t, value of type t arrow nat, etc. Okay, so the idea is if you're going to be a client of the counter module, then what you do is you say, I would like to use, for example, the unary implementation of type counter, and I'm going to make a variable here, which I could have called something other than t, right? I might have called that c, in which case all through here I would have c's instead. I make a local variable standing for the type that was included in the package of code. And then I use all of the functions, 0 increment value, with that corresponding type. So what we're saying is you open the package, coming up with a name for the hidden type. Yeah?
So is open the same as unpack?
Yes. So I mean, this, I forget what's in Bob's book. This gets called unpack and lots of other things. Yeah. I mean, you could almost just call it let or something like that, right? So like all of these basic operations have many different names. Yeah, but so you're unpacking the existential. Okay? And the idea is that what you're doing is you're saying that I would like to use the private implementation in then some pieces of code, right? So this might be some code where for logging purposes, you're trying to count how many times an operation occurs or something like that. And so you start off with a 0 and you call increment on it a bunch of times and eventually you get a value. Okay? And so E1 here is the sum implementation. E with t and x free is the code that uses this kind of stuff. And then the condition that sigma is a type not dependent on t and on t says that the abstract type doesn't escape the open. So you're not allowed to return something that includes a t from the whole open. You have to be done with your use of the private module by the end of the open block. Okay? And note that this will type check. If this type checks for unary colon counter, then it also type checks for binary colon counter, because right here, all we want to know is that this has type exists t dot tau, and both of those have type exists t dot the implementation of a counter. So the idea here is that the client code is polymorphic in the representation of the abstract type. Right? The client code doesn't care how you implemented the abstract type. It just says, I'll work with respect to whatever t you happen to have picked. Okay? So now the last thing I want to do is to talk about what we would want to reason about with this kind of code. And an example of the kind of reasoning that we would like to do is to say that, let me write UC for my unary counter. It should be the case, if I've done things correctly, that my unary counter and my binary counter are observationally equal. In the type exists t dot stuff that defines counter. Right? That's the intention I have in mind when I make two implementations of the same interface, one that is the slow reference implementation and one that is the optimized implementation. My idea is that somehow those should be the same. In particular, this means no client can distinguish between them. Okay? Intuitively, why is this true? There's two facts we need. The first is what we just said, that client only uses the exposed operations, right? If the client opens the unary counter, it can't do an operation on a counter that only applies to a nat. If the client opens a binary counter, it can't do an operation on the counter that only applies to a list of bits. It has to only use these operations, 0 increment in value, because C here is a type variable, which means that the type of the representation of the module is held abstract in the client code. Okay? So that's point one. And then point two, right? So this is kind of the idea that the client is a context that accepts values of this type. Point two is that we want to argue that the implementations are observationally equivalent. That is, they behave the same. Okay, so somehow we want to argue point two, my one implementation does the same thing as my other implementation. And because of that, any client, which is a context accepting one implementation or the other, behaves the same on the two values. Okay, so what does it mean for that module implementation to behave the same as that module implementation? So there's an immediate sticking point here, right? Which is that when we were proving that things behaved the same yesterday, we were proving that they behaved the same when they were two things that had the same type, right? So we could say things like, they run to the same value. The unary counter and the binary counter will never have the same value because one's represented by unary numbers and one's represented by binary numbers. Yeah, so we want to set up some notion of equivalence. And to foreshadow this afternoon, the key idea is to choose a simulation, I'll call it relation between unary counters and binary counters that is preserved by the operations. Okay, so what do I mean by choosing a simulation relation? What I mean is that, simulation doesn't mean anything there. It's just kind of for intuition. We want to say when one unary counter represents the same conceptual counter as a binary counter, right? When is it the case that they are the same, store the same information? If we think of the unary counter, if we think of counter as a machine, and you have machine states, the type C represents machine states, and the operations sort of transition in a little automaton or something like that. When do the states of the two machines correspond? Okay, so if we have K, which is a unary counter, and that is, i.e. an int, and B, which is a binary counter, i.e. a list of bits, when is it the case that they are sort of corresponding machine states? Yeah, so we could say that the value of K is equal to the value of B, and I'll write, I guess, B value or something there. Like, let me just call that piece of code the binary value. And then because the unary value is the identity, I'll just leave that off and say they're the same if when I take my binary number and convert it to unary, I get the same thing, right? So the int counter storing 7 is the same as the binary counter storing the binary representation of 7. Okay? So now, this is an idea of when the states of the machine correspond. What should we need to prove in order to know that no client can distinguish these two implementations? Well, what can a client do? A client can start at 0. It can call increment a bunch of times, and then it can take the value of the counter, right? The client has only those operations at its disposal because the client is polymorphic in the implementation type. Therefore, it can only do the things that are exposed in the definition of the existential. Okay? So it suffices to show that the simulation relation is preserved by the operations, which means it's something we'll have to spell out on a case-by-case basis until this afternoon when we sort of say what logical equivalence means for this language, which will codify all of this. But just to give you an example to boot up for this afternoon, here's what it means for this specific example. 1, we want to say that the unary counter's 0 value is related to the binary counter's 0 value. Okay? So unary counter 0 is related to binary counters 0. So what is unary counter 0? It's the 0 natural number. What is binary counter 0? It's the empty list. Why are these related? Well, what would it mean for these to be related? It would mean that 0 is the value of the empty list, which is true because we define the value to be the sum of all of the powers of 2 weighted by all of the 1s in the number. There's no 1s in the empty list. Therefore, the empty list represents 0. Okay? Okay. Point 2 what does it mean for the unary counter's increment to be related to the binary counter's increment? It means if k is related to b, then incrementing k is related to incrementing b, where that's the binary increment and that's the unary increment, right? So if I start with some two related machine states, a counter representing 6 over here and a counter representing 6 in binary over there, and then I apply the addition function to this one, which takes a successor, and the addition function to this one, which does that little loop and adds to the bits, I need to know I get related things. I.e., what we need to show is that if k is equal to the value of b, then the successor of k is equal to the value of the binary increment of b, and using that equality assumption and replacing k, what we need to show is that successor of the binary value of b, the binary counter value of b, is equal to the binary value of binary increment of b. Okay, so expanding out the definitions, right? So this afternoon we'll give you kind of the systematic account of what's going on here. If you specialize it to this case, it gives you a really natural proof obligation, right? Which says that if you do an increment on a binary counter and then convert it to unary, that's the same as converting it to unary and then taking the successor. Okay, so that's what we need to prove there. And then 3, what we need to show is that the unary counter's value is related to the binary counter's value. Well, what does that mean? That means that if k is related to b, i.e., k is equal to the binary value counter's value of b, then k is equal to the binary counter's value of b, which holds by assumption. Okay, so the value function preserving the relation will turn out to be immediate because we essentially define the relation to mean that the two things are related by the binary counter's value function. And I guess we need to do like the beta reduction that the lambda xx that's coming from there reduces to there. But we'll get techniques on the table in the afternoon to get that going. OK, so high level, here's the picture. You have an interface. You have two implementations of it. One of them is easier to think about, right? We're taking that unary counter to be the definition of what a good counter is. One of them is faster or more space efficient or otherwise clever. You want to show that no client can distinguish between this faster one and this original one. What you do is you set up a relation between the states of the two machines and then show that the initial states are related. When you take a transition, they're related. And any observable value of some other type that you kick out is in fact equal. If you do that, it establishes a logical equivalence, according to the definition of logical equivalence that we'll talk about this afternoon, between the two implementations. Therefore, any piece of client code, which is a context accepting values of this module type, this existential type, cannot distinguish between them. So any piece of code that you run on the reference implementation behaves the same on the fast implementation. Okay, so in Bob's lecture this afternoon, we'll set up the actual machinery that gets this to work. Okay.
So it seems like you were sort of intuitively thinking of this as a transition system.
Yeah.
Is there a way to make that more formal?
I mean, like,
on a record type, right?
yeah. I mean, not all abstract types are sort of straightforward transition systems like this, right? So like a binary search tree or something like that has lots of different transitions. So I don't know a way to make it more formal than that. Yeah.
Okay.
Yeah, I mean, it wasn't like a transition system in the sense of like stepping, right? This is just like, we're writing some code that I'm just thinking of the elements of the abstract type as states of some sort of machine for sort of intuition. Yeah, yeah.
Just to double check. So this idea works for any relation at all that is preserved by the operation?
Yeah, I mean, Bob will get formal about exactly what conditions you need here. So basically, where I'm writing equals here, really I'm going to mean observational equivalence. And there's going to be a notion of relations that you're allowed to pick here. And the main condition is that they respect observational equivalence. And that will, by definition, yeah. So we'll, yeah, like this was like why one might want to do the stuff we're doing in the afternoon. And then the stuff in the afternoon will fill in the technical stuff. Yeah. Yeah.
So I was wondering, so for each such abstract type,
Mm-hmm.
do you have some kind of test way to, that is called, for example, whether to
So it's not necessarily a decidable property, right? Like you can't automatically test that this function commutes with successor like this, right? Because that's a proof by induction. So what we can do is we can automatically generate the proof obligations. So this 1, 2, 3 that I showed you, I kind of invented by unwinding some definitions. But then when you get down to this is like some arbitrary equational reasoning, which is not going to be a decidable property in general. Anything else?
So it seems like in the setup of the packages,
Yeah.
that you could achieve the same with the universal type instead of
Mm-hmm. Yeah, OK. So this will be in the hands-on session. Exists t dot tau adds nothing to system F. So you can define existentials in system F in such a way that these two rules and the step rule that I actually didn't have time to write are true. So that'll be an exercise, which is to show that, in fact, all of this is already there. OK? Yeah, so you're exactly right.
So when you say that you are going to choose a simulation relation,
Mm-hmm.
necessary to choose this relation, can't we just say that there exists some relation and then prove equivalence?
Well, I mean, we are proving that there exists some relation, but how do you prove that there exists something? You have to pick a specific one, right? So like at various points in this reasoning, we used the fact that the definition of the relation was blah in order to say that this condition unpacks to this, and then I'll prove this by induction. So if I didn't know what the, I mean, you need to establish that there exists one. The easiest way to do that is to pick one and show that it has the right property. But you could use other means to argue that one exists too. OK. Oh, what?
So I can use that simulation if I have a specific implementation and an abstract one. If I want to say something about all implementations, like at the same time, all well-behaved implementations, I guess I could just do that via...
Yeah, I mean, so you could always suppose an implementation of the existential that is related to a reference one, and then reason about that. You could, yeah. So like that's a good way to say any correct client does blah, right? So like if I say, suppose I have an implementation whatever counter is related to unary counter, then I could prove things about whatever counter by proving them about unary counter. Yeah, so I think that might get that kind of thing. OK, let's pause there and do the coffee break. Thanks.